your recorder should be available. Okay. Okay, so it is Thursday, our last lecture before your weekend. So let me go into this subject, which is fixed first law for binary mixtures. The objective of today's lecture is basically understanding Fick's law for diffusion and binary isothermal isobaric mixture. So that's the main objective of today's lecture. To do this, what should we do? So I introduced you Fick last lecture on Tuesday. So you know the gentleman who was in front of you. It is his equation is actually for binary mixture. So because we have to start with simplicity, and simplicity means you start with simple system. So simple system is binary mixture. Then you have to put the ground. What are the assumptions? So the assumptions basically, it's isothermal system. Isothermal means what? From thermo?
Constant temperature.
Constant temperature, exactly. Isobaric?
Constant pressure.
Constant pressure, perfect. And the equation for binary isothermal and isobaric system is given to you as JAZ equal to minus DAB dCA over dZ. So basically here, when we say J, you remember last lecture what we said the J means? J means what?
Molar diffusion flux.
Exactly, diffusion, molar diffusion flux. And we are speaking about A, because there are two components. One of them is A, the other one is B. Okay, so the molar diffusion flux for A equal to negative DAB. DAB is actually defined as, it's called diffusivity, or we can also name it as diffusion coefficient. Okay, so capital D is basically diffusivity. Sometimes I call it diffusivity, sometimes I can call it diffusion coefficient. Both of them are correct. The subscript for D is AB. So the binary system AB. But here actually means something else as well. Means A into B. You see? Yani B is the solvent and A is the solute. So D of A into B, diffusivity of component A into B. dCA, derivative of change in concentration of A, that will be your driving force, and the distance will be the delta Z. So simply as this. So if I ask you, what is the unit for the diffusivity or diffusion coefficient of 1 into 2, of A into B, what will be the unit? Any idea? Or can you find it yourself?
It's length squared per time.
It is unit of length squared per unit time, but for people who are still not awake, the diffusivity, you can get it from the equation. The molar diffusion flux has a unit of what we said? Of moles per area per time. So basically here, it's moles per liter per length square per time. You have also, you can take the dz up and the dCA down and then you can be the diffusivity here will be on one side of the equation. So the concentration is basically the moles per unit volume. So that means LQ, and the delta Z will be the length. So if you cancel out identical unit, then you will be left with a unit of length square per unit time. So the unit of diffusion coefficient is basically centimeter square or meter square per second. So that's that.
Doctor, I have a question.
Yes.
The small c at the A, what does it denote for, and what does the DZ denote for also?
The small z, you mean here?
Yeah. Yes.
Okay, and the direction of z.
Ah, all right.
Okay, whereas here the z here, it means the distance, okay?
All right.
So the diffusion coefficient, the D, AB, we mentioned it earlier, depends on few factors. One of them is the pressure, the temperature is the second one, and the composition of the system is the third one. Remember, when we laid the ground for the Fick's law, it was isobaric and isothermal system. So we are assuming that pressure and temperature are constant. Third element is the composition of the system is also important. How much A is there? 20%, 30%. Each one of them has different coefficient, diffusion coefficient, surely, than the others. How can we find this diffusion coefficient? We can find it using experimental values. Okay? Now, somebody has gone into the lab and he found the experimental value of diffusivity for the three phases, for gases, for liquids, and for solid, and he put it as an appendix. For us here, we are just going directly into the system, and from the appendix we can find it. But somebody else has gone to the lab and did all of those experiments. So let's have a feeling about these numbers for these phases. Diffusivities for gases, it will be in the range of 0.5 to 1 10 the power minus 5 meters square per second. If you use the SI unit rather than the centimeter square, directly the meter square, the power of the 10 is 10 the power minus 5. If you come to the liquids, is around 10 the power minus 10, 10 the power minus 9. If it is solid, it becomes 10 the power minus 14, and it becomes 10 the power minus 10, that range for the values of diffusivities. So you can see the ranges for diffusion coefficient for different phases. Okay, so if you now didn't find whatever you want in the experimental experimental data which is available in the appendix, what to do? Well, there is another way to do it, which is using mathematical expression. So they are called semi-theoretical expressions. And they have been developed by scientists to find, to give you a kind of approximation, because experimental value is giving the real value, the exact value. But, okay, if you don't have it, then what to do? The answer is to use some expressions that you will use it in this chapter to find the diffusion coefficient. So that's that. Okay, let's see some of these values in the appendix. So in the book that you have, basically binary diffusion coefficients is given tabulated in table A1. And the first one, A1, is mass diffusivity and gases. You can see also sometimes called diffusivity, sometimes called diffusion coefficient, sometimes called also mass diffusivity. All of them are same. So if we look at the first system here, air ammonia, okay, air ammonia, and temperature is 273, okay. The diffusivity or mass diffusivity is 2.006. First of all, you see there is in the D there is A and B. So which one is A? Which one is B here for air ammonia?
I suppose A is for air.
Uh-huh. We
Or
said
which option?
solute and solvent.
All right.
Okay,
So
so
A is for ammonia and B is for air.
yeah. So ammonia into air, yani that's air will be the solvent, and ammonia will be the ammonia will be the solute, air will be the solvent. So A will be ammonia, B will be A. So the rest will be same: aniline, benzene, bromine, etc. CO2. You have also other system: ammonia, ethylene here down, carbon dioxide, benzene system, carbon dioxide, ethanol system, hydrogen ammonia, nitrogen ammonia, oxygen ammonia, and the temperatures are given to you because we said the temperature is important. It's influencing the value of the diffusivity. Now, what is the unit for this diffusivity here? 2.006. Can you see it? I cannot magnify it, but can you see it?
Yes.
You can see also. Okay, we can see, make it bigger. Okay. So what is the unit here?
Meter
It's
square into Pascal
Per,
per
per
second.
second. Yeah. Well, we mentioned it's supposed to be meters squared per second. So why we are having the Pascal here?
because the value of pressure was not given.
Because there was what?
The value of the pressure was not given or added to the calculations.
No, it's actually added. Anybody else
They
can tell
assumed
me?
it. They have might been assumed it as an ideal gases.
Now, my question: why the unit is meters squared Pascal per second? That's simple question. Uh, it was supposed to be meters squared per second. That's the diffusivity. I already mentioned this. But why here in this table it is given to meters squared Pascal second? I think I magnified enough. Yeah. Any guess?
Maybe it's gas. I don't.
Surely it is gas because that's gas. Okay. Because look at DAB. Is it DAB only?
It's DABP,
So it is multiplied by
pressure.
pressure. So it's because of that actually. So if you want to find the DAB only, you have to divide by system pressure. Because you mentioned at one stage it is isobaric. That means if the pressure of the system is given to you and you are supposed to find experimental value from this table, then the 2.006 you have to divide it by the pressure in Pascal to get the value of DAB. I think this is clear, yeah?
Yes.
Okay. Now we can come also other things. This is basically mass diffusivity in the liquid at infinite dilution. Okay. What's the meaning of infinite dilution? And why it is at infinite dilution? The answer is, well, we are assuming, as I mentioned, the simplest cases. And we want to remove any interaction between the molecules. Okay, to do that, you have to assume, we mentioned assume temperature is constant, pressure is constant. Another thing is the dilution. It is dilute, and it's not concentrated liquid, it is diluted, very diluted liquid. Okay, so that's the case that these values are given to you. So if you have chloroform acetone, for example, we mentioned that A will be acetone, B will be chloroform, and temperature is 298 Kelvin. The value of DAB is 2.35. Okay, correct? Centimeters square per second, or I'm missing something? So if I say to you the value of chloroform acetone system is 2.35, is that correct?
It has to
No.
be 2.35 into 10 raised to minus 5.
Yeah, that should be multiplied 10 to the power minus 5 centimeters square per second. And remember the range of the values that we gave you. It was in meters square per second, so you can double check things. So basically, this table shows you the system for liquids, and the diffusivity. You see on the diffusivity there is a kind of circle on the top of diffusivity. What does that mean? Usually,
Initial?
sometimes called initial. Sometimes actually it's an infinite dilution. This is the reason you have D naught. Okay. There are also other systems, for example, benzene, acetic acid, benzene, ethanol, yani acetone, acetic acid, ethanol, water, ethyl acetate, and water and others, aniline, ammonia, yani acetic acid, etc. Different systems has been already given to you. The last case is, or the last one is for the solid state. Hydrogen and iron at different temperatures is given to you as directly the diffusivity in centimeters square per second. You can have, for example, aluminum and copper at a very high temperature is 2.2 10 to the power minus 9 centimeters square per second. Okay? So another system that you can always go back and see from the tables. Okay. Okay, our last actually slides will be about an example. The example is basically telling us that there are two bulbs which are connected by a tube. Two bulbs, like two balls, okay? If you look here, you have two bulbs here, these two. And it is connected by a tube, okay? The diameter of this tube is 0.002 meter in diameter and 0.2 meter as a length. And تقريبا 20 centimeter, and the diameter is quite low as well. Bulb 1 contains argon and bulb 2 contains xenon. Both of them are inert. The pressure and temperature are maintained at 1 atmosphere and 105 degrees centigrade. The diffusivity is 0.18 centimeters square per second. So he gave you the temperature, the pressure of the system, and also gave you the diffusivity for the gases. At time t equals 0, initial time, diffusion occurs between the two bulbs. At a later time, the argon mole fraction at end one of the tube is 0.75 and zero point 0.2 at the other end. So he gave you also the composition here. Determine at the later time the rate and direction of mass transfer of argon and xenon. So he wants you to find the rates of mass transfer and the direction of mass transfer. Also, the R, the constant, is given to you, 82.06 centimeter cube atmosphere per Kelvin mole. So that's the whole question. It's given to you like that. Anything about this question you don't understand before we move on? I think it's clear what's happening in the next slide. So you have one of them, argon on one side, xenon on the other. You open it. So what's going to happen? You have molecules of xenon moving this direction and argon moving to the other direction. So that's the direction, and they will mix. And what he said, at a later time, the argon mole fraction at end one, it was 100%, is 0.75. It reduced to 0.75, and the other end, it will be 0.2. That means here 0.2 argon, 0.8 xenon. The other one is 0.75 argon, 0.25 xenon. This is what it implies. So he wants you to calculate the mass rate and the direction. Okay, how to approach this question? We have to use the equation which is at the bottom. You see the equation here, Na. You see my mouse, yeah?
Yes, doctor.
Okay, great. So basically this one, Na, you see this equation, Na, CdA XA delta Y over delta Z. From where I got this equation? I have to go to the beginning. Let's remind ourselves, this is the equation, which is basically the flux, which we said the Fick's law. So if you want the flux, we said the unit is mole per time per area, okay? And diffusivity, then you have change in concentration and change in distance. So if this is the case, okay, so Na basically is what? Mole per second, okay? Mole per second. It was supposed to be divided by A. A is actually now, what is A? What is A, we said?
Argon?
No, the A, area. A is area.
The
Capital
area
A.
of the bulb.
Well, this is also a bit of thinking you need.
Area of
Which
the
kind of A? Sorry?
tube?
Actually, here you should pay attention of which area we are implying. The area is basically, you know, it is here is defined for you. You see, A equals 3.1410 the power to 0.2 square divided by 4. What is this area here?
Of the tube.
It is the tube, yeah. Okay, but is it the whole tube or part of the tube? It has a name actually, this area, and you should pay attention to. It is the cross-sectional area. Okay, so the A is basically the cross-sectional area. So cross-sectional area of that tube is pi d square over 4. You take a section of that tube. Okay. So if you do that, that area will be 0.0314 centimeters square, and you have to be careful about the units from now on. So you usually, if you are going to use this centimeter, and everything else should be centimeter. So the area here is centimeters square. Then in the equation down, okay, we found the A. What about diffusivity? It was given, yeah? It is 0.18 centimeters square per second. So diffusivity was given. So that's 0.18. Remaining is also delta Y, the change in mole fraction. So 0.75 minus 0.2 for argon, because we are finding it in A. Delta Z is the 20 centimeter, which is the length, okay, of that tube. One more variable that you have to understand and calculate. طبعا, since this is gas, then you are supposed to assume it is ideal gas situation. In that case, you can find the C here, which is basically depends on the unit of the R. Since the R was in centimeter cube atmosphere per Kelvin mole, then the pressure and temperature should be same. So that means 1 atmosphere and the temperature is 378 Kelvin. If you do that, then you will get the unit of mole per centimeter cube. If you put all the numbers here now, you will find the mole rate, okay, which is 5 to the power minus 9, which is from argon moving from bulb 1 to bulb 2. So that's the direction and that's the rate. What about the other gas, which is xenon? Well, it is exactly the same as a rate, but it's moving from bulb 2 to 1. Can you prove it? Yes, you can prove it. You can put again the numbers here, and you will see that it will be 5 to the power minus 9 mole per second. And definitely it is moving from high concentration to low concentration. Okay? Any question here?
No questions.
No, doctor.
Okay, my last slide is actually, it's about cinema, I think, yeah? It's about cinema with the popcorn. Oh, it's not, actually it's not about cinema, it's about YouTube. Well, I already put the link, the slides on the blackboard. I need you to go and look at the YouTube. Do you want to spend now 10 minutes with me, or you can watch it later yourself? It's only 9 minutes, I think. It will show you actually Fick's law very nicely. I think it's Khan Academy. It will show you this law, what is happening regarding the transfer, the movement of the molecules. Very nice. I think everybody can watch it himself in his own comfort, because it's very easy, very nice, shown to you. I don't believe there will be any questions, but if you want, I can go through it with you. I don't know, just let me know. How to close this? Okay, since you are quiet, share application screen. But okay, I need to go there in that case. Just one moment. Yes, one moment.
ينفع مشروع ولا لا؟ هل اونلاين ولا بلاد؟
Okay, let me share my screen in that case. Share. That's it.
This is a quick video over Fick's law of diffusion. Now,
Are you able to watch my screen?
Yes.
Yes,
Okay.
doctor.
Okay. In that case, let's play it.
diffusion is explained, where if you have a high concentration of something, it will go to a low concentration. Fick's law of diffusion describes that. So let's say we had some area. And what he said is, well, he basically just measured, he measured the number of A particles crossing this area per time. So we had the number of A particles crossing an area per time. And he called this flux. And that is equal to J A Z. So A is just the A just represents whatever's crossing it, and the Z, what actually means going in this direction, in the Z direction. So it's the flux of A in the Z direction. And he actually was able to make an equation for it, where it was the negative diffusion coefficient of AB. So this is A and that's B, times change in concentration of A per change in the Z direction. So then another way of writing that is the negative diffusion coefficient of A into B times delta C over delta Z, where delta Z is just equal to, let's say if we start right there, this would be Z1. So, and this would be maybe be Z2. So Z2 minus Z1. And this D right here actually means an infinitely small area. So if you actually move the delta Z2 maybe right there, an infinitely small change. But don't worry too much about that. It just means is Z a positive or negative number? And for our case, it will always be a positive number. Positive number. What about this DC? Well, DC means, well, C is just a concentration. So this is A is in a high concentration. And it's going to a low concentration. So we'll call this C1 and C2. So then what is delta C? Well, delta C is just equal to C2 minus C1. And this is a high concentration or a large concentration. So this is actually going to be, the delta C is actually going to be a negative number. And that's actually why there's a negative right here. So if you have a negative DAB times a negative number over a positive number, you get a positive number. So that is the purpose of this negative, so that the flux of A in the Z direction is positive. So what exactly is this DAB? Well, it's actually unique to the two particles. If maybe B was bigger, it would be different. If A was bigger, it would be different. You can't say I know the diffusion coefficient of oxygen. You have to say, I know the diffusion coefficient of oxygen into B, or I know the diffusion coefficient of oxygen into nitrogen. You cannot say you know the diffusion coefficient of oxygen. You need to know what it's diffusing into. So that is what D represents, or DAB. It represents the diffusion coefficient, and it's unique to each one. It actually is what gives the speed of how fast something is diffusing. This is the speed, you can think of it. And it actually has units of, so DAB, and actually you can just say D. The diffusion coefficient is actually area per second. And that seems a little bit confusing, and I mean for good reason, because how can you have an area per time? We know we can have like a distance per time, and that's usually what we think of speed. But why is it area? Well, it's actually due to this delta C, delta Z, where delta C is the number of ions, or usually moles, per volume, or centimeters cubed. And that's multiplied by delta Z, and delta Z is a length, so that's just centimeters. So then we have moles per centimeter times the inverse of length, or the inverse of the change in the length, centimeters, and that will give us moles per centimeter to the fourth. And that's really odd, so that's why they actually have this, where this is actually centimeters squared per second. So now if we multiplied this by D's units, we would get moles per centimeter to the fourth times these units times centimeters squared per second. So this 4 cancels out that 2, and that now becomes a 2. So then we get moles per centimeter squared per second. And that is what we said flux was. Where, again, moles is just another way of calculating the number of something is. So that's just the number of something per area time. And again, that's flux. So hopefully this was helpful. And again, it is possible, usually you just look up what the diffusion coefficient is to get your calculations. I would highly doubt that you'd be asked to find the diffusion coefficient. That you'd have to use different type of equations, but usually it's something that you're given and you look up, and you calculate the flux. And I said that was flux per area, or that was the number of something per area per time. So what if we wanted to know how many ions were traveling through this area? Well, what you would do is you would multiply the flux, J, times the area, and that would get you the number of things, or the moles per second. So if you maybe had a bag of chips, you had oxygen, and you knew what the flux of oxygen into the bag was, but that's just a small area. So flux again is just the number of things per area time. So to get the total number of things going through it, and maybe let's say 5 seconds, you would multiply it by the total area of the bag, or A, flux times A times the time is equal to the number of things going into that bag, going into it. So it's just the moles of something going into that bag. So that is Fick's first law of diffusion. Again, the